We had worksheet number 11 due for homework last night. We had a number of questions on that worksheet, 4 of which we need to go over here today. 7, 8, 11, and 12. Let's take a look at 7 and 8 first, of course. Number 7. 7 says an electron is traveling to the east through and experiences a magnetic force. The context of a magnetic field question, we got to recognize right away that we're going to use a hand rule. If this is an electric field question, then there are no hand rules, right? Remember, a charged particle in an electric field experiences a force parallel to the field. If it's a positive particle, then it will experience a force in the direction of the field. If it's a negative particle, it experiences a force opposite to the field. If it's a magnetic force, magnetic field, then we got to use a hand rule. So this is a magnetic force. We know we're going to use a hand rule. And since it's an electron, a negative particle, we're going to use a left hand rule. Okay? Thumb, fingers, palm. All right, so it's traveling to the east. It experiences a magnetic force to the north, although we're saying that's geographic north, which is really magnetic south, right? In which direction does the magnetic field point here? Okay, in which direction does the magnetic field point? It's kind of like algebra. Right? We're rearranging a hand rule here. V equals d over t. Rearrange it to solve for t. Okay, here we're saying thumb, fingers, which way does my palm point? We're going to rearrange that. Thumb, palm, see which way my fingers point. Just a little bit of algebra on a hand rule. The good news is it's easier than doing algebra using equations. So we're going to say the electron's traveling to the east. Okay, that's east, that's west, that's north, geographic, and that's geographic south. If you're in a room like the cafeteria writing your diploma exam and you get turned around because you're a little bit nervous or you're just not used to thinking about physics when you're in the cafeteria, and you have trouble picturing in your mind which way is north and south and east and west, then make it up. Okay, make it up. Let's say we're in a room right now where we can't see outside. We've just walked into this school for the first time. We're all turned around. We don't know which way is really north and which way is really south and so on. Make it up. We're going to pretend that way is north. Okay, that's north. If that's north, then that's south. And if that's north and that's south, then that's got to be west because Western Canada is the left-hand side, right? West is on the left. East is on the right. Okay, we got an electron traveling to the east. Okay, we're saying that's east. It's not really, but we're saying it is. Okay, we got a magnetic force to the north, so my thumb is going to go to the east. My palm is going to go north. My fingers are going to point up. Don't say out of the page. You could say out of the earth, but it's okay in this case just to say up as well. All right? So we pretended that was north. It's not really, but it gave us a magnetic field upwards. Let's say now that that's north, because that really is north, right? Geographic north. That's really east, really west, really south. Thumb goes to the east, magnetic force to the north. Which way is my fingers point? Up. So as long as you're consistent in your definition of north, south, east, west, it doesn't really matter if you're right or not, as long as you're consistent in that definition, right? North is that way, east is to the right, and west is to the left, and so on. So don't panic about that when you get into the cafeteria in June and you're a little bit nervous and you're having trouble figuring out which way is north. Make it up. Just make it up. Number 8, an alpha particle is traveling into the page, a magnetic force. All right, alpha particle, it's a positive particle. We're going to use a right-hand rule. It's a magnetic field, so it's not just an electric field where we know that the force is parallel to the field. Okay, it's perpendicular. And we're going to have to use the hand rule for deflection to figure that out. All right, so it's going into the page, magnetic force to the right of the page. Right hand, right thumb into the page. Palm points to the right of the page. Fingers point which way? What's the answer to this question? Good, not up. Okay, for me right now, as you look at my hand, it's pointing up, right? But we don't want to express it as up or down. We want to express it relative to the page, not relative to the earth. So it's toward, as you said there, toward the top of the page. That makes sense? For you guys, if you guys are doing it on your page, right, it's thumb into the page, palm points toward the right. Your fingers aren't pointing up. Your fingers are pointing towards the front of the room, but they're still pointing toward the top of the page. So that's why we express those ones in terms of the page. Okay, question number 7 was relative to the earth. So up is fine. This one's relative to the page, so up is not fine. Toward the top of the page is the way we express that. All right, we got two more questions to go over here, 11 and 12. 11 says an electron travels through a perpendicular magnetic field. Why is that word perpendicular important? The good news is the vast, vast, vast majority of time it will be perpendicular. But why is it important to note that anyways? Yeah, to use the hand rule and to use the equation that we learned yesterday, it's got to be perpendicular. If it's not perpendicular, you better hope it's parallel. If it's parallel, what's the force then? Heavy? Zero, good. So that's easy, right? If it's parallel, it's a force of zero. Too bad it wasn't always parallel because it would be easy then, right? If it's not parallel or perpendicular, well, you're probably not going to, well, you won't see that for sure until you're in university, if you take a physics course in university. So we don't have to worry about that. It's perpendicular, it's parallel, or you're in university, one of the three. All right, so here we got a magnetic field. Here's the magnetic force. We're trying to find out how fast the electron's moving. B, F. Here's the equation that you learned yesterday, right? Does anybody remember what that little upside down T meant yesterday? Yeah, it means perpendicular. It means this equation is only valid when they're perpendicular, but we know that they are, right? Because we just talked about that. Trying to find the speed here. Q and the B both go down, so it becomes F over Q times B. What do we got here? 4.5 times 10 to the minus 14. Divided by, it's an electron, so it's 1.6 times 10 to the minus 19. And B is 3 times 10 to the minus 1. Hey, I'm going to do this on the calculator here. It doesn't seem like a hard one, but I want to do it on the calculator anyways, just to show you one little thing. Okay, let's say 4.5 times 10 to the minus 14. Okay, let's divide that by 1.6 times 10 to the minus 19. Oops, not answer there. Exponent. 10 to the minus 9. Oh, no, that's not what I want. What am I doing? There we go. Divided by 1.6 times 10 to the minus 19 times 3 times 10 to the minus 1. Good? Press equals. 8.44 times 10 to the 4. Tara, did I see you? When I said good, did I see you kind of go like that? Why isn't it good? Yeah. Okay, this is actually a pretty common mistake, even in Physics 30. I mean, you guys are all smart people. Otherwise, you wouldn't be here, right? But yet, even smart people can make silly mistakes like this on a calculator, what I just did. And you do. Okay, you do. Smart people do make silly mistakes like this. Tara's absolutely right, though. We've either got to calculate that number on the bottom first and then divide the top by the bottom. Or what I usually do is just use brackets. So let's say 4.5 times 10 to the minus 14. Divide it by bracket 1.6 times 10 to the minus 19 times 3 times 10 to the minus 1. Is that going to be good? Yeah, it is. Now, if we had two numbers on the top that we had to multiply, it's not critical that we use brackets on the top. Although I sometimes do just as a matter of habit, but it's not critical. On the bottom it is. So what do we get there? 9.38 times 10 to the 5. That's better. That's a pretty typical speed, by the way, for a charged particle, 10 to the 5 meters per second. A lot of times you'll see 10 to the 4. A lot of times you'll see 10 to the 6. From time to time, you might see 10 to the 7. 10 to the 5, 10 to the 6, in that range is usually what you see. It is possible to see numbers that are dramatically lower as well for speed. They're just not all that common, that's all. If you get a number that's not 10 to the 4, 10 to the 5, 10 to the 6, it might be worth double checking your work. Doesn't mean you're wrong, but it might be worth double checking at least. Okay, last question we need to go over here is number 12. An alpha particle in a magnetic field again. So let's Let's circle this. We know that we're going to have to use a right-hand rule. That is, if we're going to use a hand rule to begin with, right? We're trying to find a direction here. Here's an acceleration. Here's a magnetic field. Let's find speed. Hey, there's a word in here that kind of jumps out at me. Every time I see this word, I always do something really, really simple, actually. More of a physics 20 thing. You know what it is? Yeah, the word accelerates, the word acceleration. Okay. Now, if I don't have a value for acceleration, then I don't necessarily use F is equal to m times a. But if I have a number for the acceleration, then I'm virtually positive I'm going to start off by saying F is equal to m times a. The alpha particle's mass is 6.65 times 10 to the minus 27 kilograms. And we multiply that by the acceleration, which is 8 times 10 to the 13. Does anybody have a value for that? Thank you. 5.32 times 10 to the minus 13 newtons. Small force, but it's an alpha particle. It's pretty light, right? Now we're going to say F is equal to QVB. And we're going to rearrange that to solve for V. F over Q times B. And we end up with the same issue as we had in the last question, right? Make sure when you're dividing it, you divide by brackets, Q times B. Okay, and when we do this, I don't remember what I showed you as the answer there, but I'm guessing it's going to be 10 to the 5 meters per second. Something times 10 to the 5. Is it 10 to the 6? Okay, that's pretty common as well. Not quite as common as 10 to the 5, but what's the base there, Marker? 5.58. Okay, so let's say in this question, they asked me to express this as a numerical response. They could ask me in a couple ways. They could say A decimal B C times 10 to the D. They could say B times 10 to the W. Okay, what's the answer in the first case? Well, what's the answer in the first case? A decimal B C times 10 to the D.
5. No, 5. 5, 8.
Good. And what's the answer in the second case, Joey? No. No, but you're close. What's the answer in the second case? Right. .58. So in the first case, you're just putting the digits A, B, C, D. In the second case, you're putting the number B, which includes a decimal. Does that make sense? Good news is, this is what we're seeing more often now on exams, is A decimal B, C times 10 to the D. Just be prepared for both. All right. Let's take a look at one more example here now that we've finished that worksheet. 12.2 on page 600. It says a carbon ion with a mass of 2.01, kind of hard to see that actually. I think it's 10 to the minus 26 kilograms, and a positive charge of 1.6 times 10 to the minus 19, enters a region of an external magnetic field of 6.32 times 10 to the minus 5 Tesla. What's the perpendicular speed? All right, perpendicular, we know it's moving into the page. We know the magnetic field is pointing. Hey, which way is the magnetic field pointing? Which way is it pointing? In between those two magnets. Left, right, up, down? To the right? Is that right, guys? Is that right? No, it's not right. Magnetic field points from north to south, outside of magnets, right? Points from south to north inside. Okay, north to south outside. So we got a magnetic field that's pointing to the left, a particle that's going into the page. Okay, hand rules all work. Everything that we've learned so far works because they're perpendicular to each other. Okay, good news. Find the perpendicular speed at which the magnetic deflecting force will balance the gravitational force so that the carbon ion will travel in a straight line. What are they really telling me here? What are they really telling me? Well, they're telling me that there's a downward force of gravity acting on this carbon ion. And they're telling me there must be an upward magnetic force acting on this ion, and these two forces must balance each other so that it goes straight through. If gravity was bigger, it would go curve downward. If the magnetic force is bigger, it would curve upward, right? But if they're saying it's going to go straight through, then these two forces must be equal in magnitude, at least, equal in magnitude to each other. So let's do that. Let's say Fm is equal to Fg. Now, I want to do one thing. I'm not comfortable with going straight here. You can do this, given what it tells you in the question. But I'd be more comfortable if I checked to make sure the magnetic force is upwards. We know gravity is downwards for sure. But we're kind of relying on these guys that wrote the textbook to tell us that the magnetic force is upwards. I'm not sure that I trust that. Let's just double check that. It's a negative, no, it's a positive particle. So it's right hand. Thumb in the direction of the particle into the page. Fingers in the direction of the field from north to south. Sure enough, the palm points upward. The magnetic force is upward. So they were right. Okay, it's all good. I could have got away without checking that, but I feel more comfortable now that I have. All right, magnetic force is QVB. Gravitational force is M times G. We're solving for speed, right? So it's going to be V is equal to mg over qb. Now it's just a matter of plugging some numbers in here. 2.01 times 10 to the minus 26 times 9.81. Charge is 1.6 times 10 to the minus 19 times 6.32 times 10 to the minus 5. Now, once again, that bottom number, you either got to calculate that bottom number first, or, as Tara said, use brackets when you're dividing by that bottom number. Otherwise, you're going to get the wrong answer. I can't remember what this is, but I do remember from last class that it is a very, very small number. Not a number that we would predict. Not a 10 to the 5, 10 to the 6 number. Okay, does anybody have the value for that? Which we could express if we wanted to as 1.95 times 10 to the minus 2. That is the correct answer. And in the last class, we got the same thing, I believe. In the last class, we checked with what the book said, and that's what it was. Okay, if this is an exam, and I get 10 to the minus 2 meters per second for a speed of a moving charged particle, it doesn't mean I'm wrong. I'm not wrong. It's right here. Okay, but it does mean that I might go back and check my work, because I don't like 10 to the minus 2. It's a small number. Usually for charged particles, we get speeds that are quite a bit bigger than that. That's all. Okay, it is right here, and it could be on your exam too, but it's worth checking. Okay, I'm going to have you work on one question that goes along with this. Question number 1 here on page 600. See what you can do with that over the next couple minutes. If we're good with that question, we're going to take a look at a multiple choice question now. This is number 72 in your worksheet booklet. It says, you get electric field, gravitational field, magnetic field. Okay, one of these is electric, one of these is gravitational, one of these is magnetic. You want the particle to deflect downwards. Which field is which? That's what they're asking you. Okay, I'm going to ask you to do this at your desk right now. Don't bother submitting it because our Wi-Fi is a little choppy this morning. Just do it, and then once everybody's finished, we'll take a look at it. Let's take a look at this one now. It says the electron is deflected downward in each field, then fields 1, 2, and 3 must be what? Listen, when we started this question, I saw right away a lot of you taking your hands out and doing hand rules, and that's fine. Okay, you're trying to find the direction of a magnetic force and so on, of a charged particle moving to the right and so on. That's fine. But you know what? That's not what I do first. Okay, we got 3 fields here, gravitational, electric, and magnetic field. And I don't think magnetic field is the easiest one to deal with at all. I think it's the hardest one to deal with. That's the last thing I would do. Okay, the first field that I would deal with would be gravity. We got a charged particle Doesn't matter if it's charged or not. If it has mass, it's going to experience a force in the direction of the field. We want a downward force on a mass. What kind of field, what direction of a gravitational field do we need to have a downward force? Downward. So it means that this one's got to be gravity. Okay, we don't have to do any hand rules to figure that out. We don't even have to figure, does it move with the field or against the field? It's always the same way as the field. So if you want a particle to be deflected downwards, then the field has to be downwards. For sure, that's gravity. All right, the next easiest one I would say is the electric field. So ironically, the one that we've been dealing with is the one that I would save till last to do. If we want a negative particle to experience a force downward, then which way must the field be? Upward. Because positive particles experience a force, an electric force with the field. Negatives are against the field. So we want our field to be upward. This one's got to be electric. And finally, this one must mean this one's magnetic, but let's just double check that just to make sure that I haven't made a little mistake there. This is where we're going to use the hand rule, right? It's a negative particle, thumb in the direction of the particle to the right, fingers into the page in the direction of the field, palm points downward. So we're going to say that this would be magnetic field. So we got electric, magnetic, and gravitational field, and thankfully, most of the class picked A, which is the correct answer there. Good. Let's move forward here, guys, and extend what we did yesterday. Not replace what we did yesterday, but extend what we did yesterday. We talked about the charged particle in the magnetic field. Let's draw a magnetic field here into the page. That charged particle, we'll make it a negatively charged particle moving to the right. We know that that experiences a magnetic force, and we can find the direction of that magnetic force by the hand rule for deflection, and we can find its magnitude by using the equation QVB. We know we can do that because it's moving perpendicular to the field. We're not going to throw that out. We're still going to keep that. That stuff is still completely valid. But you're going to see in a moment, there's also something else that's valid beyond what we did yesterday. You just didn't know it yesterday, that's all. I'm going to make a little key up in the top right-hand corner, top left-hand corner, I should say. Okay, green is going to represent velocity. The speed, or the velocity of the particle, in this case right now, is to the right. Red, we don't have any red drawn on there yet, but when we do, red is going to represent magnetic force. So if you see a green line, it's velocity. If you see a red line, it's magnetic force. Let's draw a few more field lines in there, actually, so we get a little bit more space. All right. Let's right now look at what happens to this particle. Which direction is the force acting on this negative particle right now? Okay, everybody with your left hand, because it's a negative particle, thumb in the direction of the particle, fingers field, palm points downward. So there's a downward magnetic force. Let's draw a red arrow downwards. Now, if somebody's walking across the front of the room up here, walking towards the right side of the room, and I push them towards the back side of the room, it doesn't mean they go straight back, right? You're walking this way, I push you this way, where do you go? Kind of like that, right? So this negative particle is also not going to go straight downward, according to this red arrow, but it is going to be influenced downward, so it's going to end up going somewhere in between. Maybe down here. Now let's figure out what direction the force is acting on this particle now. Thumb in the direction of the particle, down and to the right. Fingers field, palm points, oh, there we go, this way. Where's it going to go now? Oh, in between, right? In between the force and the velocity. So its momentum is taking it down and to the right. It's the force wants to pull it back down and to the left. So it's going to end up going down here somewhere. Thumb, fingers, palm points to the left. All right, there we go. Another one, it's going in between, right? Thumb down and to the right, fingers, you got to twist your body around here. This is where you don't want to have a rotator cuff trouble is when you're trying to do this. Thumb, fingers, palm points, up and to the left. We can keep going. We don't need to. What do you notice about this? Do you see anything that kind of strikes you? I do. Of course, I've seen it a million times before, so I should see something that strikes me. Yeah. Yeah, looks like it's going around in a circle, doesn't it? Looks like a circle. How do we know for sure that it is a circle? Because I mean, I've got 4 points drawn there, and it looks like it's kind of circular. But what is it that tells me for sure that it's going in a circle? I mean, if I had 1,000 points there, then it would be a lot easier to see, or a lot easier to say with certainty this is a circle. I don't have 1,000 points. I've got 4, but I can still say that this is going in a circle. What is it that tells me that? Yep. Good. The force is pointing toward the center. What do we call that force that points toward the center? Anybody remember? Centripetal force, right? It experiences a magnetic force always. That magnetic force causes a centripetal force, right? Centripetal force that points toward the center. It's moving in a circle. Sorry, I was having trouble spelling circle there for a second. It's moving in a circle. And you know what? It will always move in a circle as long as it's moving perpendicular to the field and as long as either the velocity or the field isn't changing, or I should say the speed of the field isn't changing. As long as everything's remaining constant and it's perpendicular to the field, it's always going to move in a circle. And all those questions you did on the worksheet, they were going in circles as well. You just didn't need to know that. It wasn't, wouldn't say it wasn't relevant, but it wasn't important for us. We had enough data to solve the problem without knowing that it was moving in a circle. The problems you're going to see today, we're going to need to know that it's moving in a circle. Now, it doesn't mean that the stuff we did yesterday you can't do today. It just means that you're going to need a little bit more today. That's all. Yeah. So here's what we had yesterday, besides the hand rule. We had Fm is equal to QVB. Find that on your data sheet. Find that equation on your data sheet. It's not a particularly difficult one to find. Where is it? Kevin, you find it? Yeah, middle section near the bottom right, under electricity and magnetism, F is equal to QVB. Okay, good, there. The next equation that we're allowed to use now, and this is a new one, well, kind of new this year, F is equal to mv squared over r. Why can we use F is equal to mv squared over r? Yep, because it's going in a circle. So we're allowed to use what we did yesterday, but now we're also allowed to use this other equation, F is equal to mv squared over r, the centripetal force equation. Find that one on your data sheet. Oh, and the search goes on. Can't find it, can we? Because it's not there. That one's not on your data sheet. Okay, that's the bad news. The good news is you can kind of get it from what's on your data sheet. On your data sheet, you're going to see this. Centripetal acceleration is v squared over r. You're also going to see this. A is equal to F over m. If you put those two together, right, F over m equals v squared over r, and you rearrange that, what do we get? F is equal to mv squared over r. So it's kind of there, but you got to put a couple equations together to do that. Hey, a word of caution here. Because it doesn't appear on our data sheet, a lot of people will just remember that equation, and that's fine. That's what I do, honestly. I don't go back to my data sheet and derive it every time. I just remember it. But if you are going to remember it, then be really, really careful, because I'm going to show you a mistake that a lot of people will make when they try to remember this, and it seems silly. You're going to look at this and say, I'll never make that mistake. Some of you will. Okay? Some of you will, unless you're really, really careful. It's End of June, you're writing your diploma exam, you've been writing for 2 hours and 12 minutes, you've got 18 minutes left, and you're thinking, I don't know if I'm going to finish this exam. You're a little bit stressed, and you come across a question like this. It's pretty straightforward and pretty easy. But then when you go to write down your centripetal force equation, because you're stressed, because you think you might run out of time on your exam, you do this. 1/2 mv squared over r. It seems silly. You're thinking right now, there's no way I will ever do that. But some of you will. You're going to get mixed up, kinetic energy. Okay, because it's like mv squared, right? With centripetal force. Okay, clearly that's wrong. Okay? We know that's wrong. We all know that's wrong. We all understand that. It's just a matter of being careful to avoid the mistake that people make. Right? mv squared over r. Now, of course, we're also allowed to do this. Set them equal to each other, because in the end, centripetal force is the force that goes in a circle, causes to go in a circle, but it's caused by the magnetic force, so they've got to be equal to each other. Use whichever one's convenient for you. Use whichever one works the best. Okay, this is what we did yesterday. This is what we have now. My rule of thumb on this, which one do you try first? Really, it doesn't matter. Try whichever one you want first. If it doesn't work, try another one. But my rule of thumb is, if you see a variable r in the question, try this one first, the combination. If you don't see the variable r, try this one. Now, sometimes you might try this one or this one and find, oh, it doesn't work for me. And you got to go to the middle one. But generally, if you don't see r, then this is what works. Generally, if you do see r, usually, this is what ends up working. All right, let's try a practice problem. Or an example question, I should say. This was not in your book, unfortunately, so I'm going to ask you to copy this one down. All right, so the question says the electron is moving at this speed, 4 times 10 to the 5 meters per second, to the right through a magnetic field that's into the page. Okay, everything's perpendicular, that's good. Particles moving this way, magnetic field is this way. Perpendicular means everything that we've learned over the last couple of days, including what we just learned about the whole circle thing, is applicable here. And we just got to see which equation seems to work the best. All right, we want to find the radius of the path and in which direction it will bend. In other words, is it going to be deflected upwards or downwards? Is the circle going to go like this, upwards, or is it going to go like this, downwards? All right, let's circle a few givens here. First of all, I probably should have circled that because it's an electron. It's a negative particle. I know I'm going to use a left-hand rule in that magnetic field. I got a speed here. I've got a magnetic field. And I'm looking for a radius here. So which one do you want to start with here? Looking for a radius. Which one do you want to start with? 1, 2, or 3? There's no wrong answer here. They're all valid. There's no wrong answer. You can start with whichever one you want, but there's one that's going to work for us more often than the others. Yeah, try 3. Hey, that's the one that I said if you're looking for R, probably start with that one. No guarantees, but it's the most likely to work right away. Fc is equal to Fm, and we know that Fc is mv squared over r, not 1/2 mv squared over r. QVB. Hey, look at this. I get 2 V's on the left side and 1 V on the right side. One of them on each side cancels out. I don't have to do that, but it just makes life a little bit easier for me if I do. I get mv over r equals q times b. And solving for r, so let's take the r up and the qb down. So it becomes r is equal to mv over q times b. R went up, qb came down. Okay, let's put our numbers in here. Electron is 9.11 times 10 to the minus 31 kilograms. V is 4 times 10 to the 5. Q is 1.6 times 10 to the minus 19. And B is 2.5 times 10 to the minus 2. Hey, when I saw this in the last class, period 2, or period 1, I should say, something struck me. I thought, oh, hey, love it. Don't have to pull out our calculator for this one. Can we do this one in our heads? I don't have to because we did it period 1. And I remember what the answer is. Is there a little cheat that allows us to do this one in our heads, though? What's 2 times 1.6? 3.2. And then another half is another 0.8, so it's 4, right? Oh, wait a sec. 2.5 times 1.6 is 4. Well, isn't 4 divided by 4 1? So those numbers cancel out, right? What am I left with? 9.11 times 10 to the something. Now I'm just dealing with exponents though, right? 10 to the minus 31, 10 to the minus 26. 10 to the minus 26 divided by 10 to the minus 21 is 10 to the minus 5. Does that make sense? Hey, listen, if this is an exam, am I going to do that in my head? No, not a chance. I'm going to use my calculator for that for sure, right? Just doing a little mental exercise right now. That's always good. When it's not a test day, that's always good. Now, is it going to bend up or down? Deflect, should say deflect, not bend. Is it going to deflect up or down? Well, if the magnetic field is into the page and the particle is moving to the right, then we're going to say thumb to the right, fingers into the page, palm points down. It really shouldn't be down, actually. It should be down the page, right? Or toward the bottom of the page. Good. That's initially, right? It goes down the page. Okay, because pretty quickly it's going to be going in a different direction. It's going to experience a force some other way, but initially it's going to be pushed down the page. All right? Guys feel good about that? All right. We're going to have ourselves a little quiz tomorrow, not on this stuff, but more on hand rules, and maybe a little F is equal to QVB. Certainly not on the circular stuff that we've done here today. We'll check over some homework on this before we do that. Okay, but what you are going to have tonight to do on this circular stuff is a little bit of homework. It's going to be worksheet number 12. You guys get a good about 8 or 10 minutes to start on it now, and work on it during scheduled help if you need to as well. That's it.